Okay, in this video we're going to look at an indeterminate structure, and in this case the structure is a half ring going 180 degrees, and this structure is cantilevered at both ends. This is a planar structure, and in the plane of the structure we have a load F pointing downward as shown. The structure looks like it's cocked a little bit sideways because my scanner somehow didn't scan this page straight. But we have an indeterminate structure because, in fact, at this point we're going to have a vertical load. We will have a side load because of the loading F, and we will have a moment. We'll have all three pieces available on this cantilevered end, and we'll also have all three pieces available on this cantilevered end. And that's too many unknown loads. In spite of symmetry, that's too many unknown loads to be able to calculate them just from statics. So we're going to have to calculate them using a strength of materials approach, in this case a Castigliano approach. I'll slide the screen up just a little bit and we'll see the change I've made to the picture. And what I'm going to do is, on this right hand side, I'm going to replace this support with equivalent loads. And so this is the picture that I'll be working with. Okay, I've replaced this cantilevered support with a vertical load, and this was point B, so I call this RBY, RBX, and the moment at point B. And I have similar loads over here, okay, and because of the direction that I'm going to be integrating things, I'm going to be starting things at this right hand end and integrating around the circle and stopping when I get to the left hand end. I don't actually have to do any statics here. So what I have to do with these redundant loads is write energy terms caused by these loads to give me the deflection at this point caused by each of these loads. Now, each of these loads causes a different kind of deflection. If I write my energy terms and take the partials with respect to the vertical load, it'll tell me the vertical deflection at this point. If I write my energy terms and take the partial with respect to this horizontal load, it'll give me the horizontal deflection at this point. And if I write my partial energy terms and take partials with respect to this moment, it'll give me the slope at this point. Now, it turns out, because there really was a cantilevered end here, I know that the vertical load is 0. And I know that the vertical deflection is 0. And I know that the horizontal deflection is 0. And I know that the slope angle from the cantilevered wall is also 0. So I'll write my deflections for each of these, and then set those deflections equal to 0, and then solve for each of these three unknown loads in terms of the load F and geometry. Now, I put a note here that says from symmetry, okay, I know that RBY here, this Y value, not only equals this Y value, but in fact both of them have to equal F over 2. Okay, but in this case I'm not going to assume that. I'm going to pretend I don't know this RBY value and solve for it. And when I solve for it, I better get F over 2 or something has gone wrong. Now, when I'm using these loads to write energy terms, and all I'm going to include in this case is bending moments, I'm going to have a section here first as theta goes from pi over 2, but then I've got to change my equations when I cross pi over 2 because of the effect of this load F. Okay, I will always measure theta from horizontal, but when I get to this point over here and make a cut, notice I will be able to make a triangle here. Okay, and this triangle will be based on theta minus this pi over 2 angle. We'll see that shortly. And so my moments in the region between theta equals 0 and theta equals pi over 2, okay, I'm going to call that M1 of theta, moment in region 1, is the vertical load times an R1 minus cosine of theta. The moment arm would be this horizontal moment arm right here outside the triangle. And I'm going to call that one a positive moment. RBX is going to create a negative moment, and that moment arm would be R times the sine of theta, this vertical distance right here, RBX, R sine of theta, with a negative sign. And then I have a moment purely due to MB. It's negative as well. If this one is positive, that one's negative. And so that gives me a minus MB term for the moment. That's my moment in the first region. My moment in the second region, taking moments about this point, will give me all, so moment in the second region as a function of theta still gives me everything that I had in the first region. So I just wrote down m1 of theta here. That in effect includes all of these terms. But then I'm going to have a bending moment. We've got to move down and look, due to f, and the distance for that bending moment is going to equal this distance right here, this horizontal distance, and that distance is equal to the sine of this angle right here, but this angle right here is my theta, the full angle, minus this 90 degrees right here. So it's f times r times the sine of theta minus pi over 2. And let's see what that looks like. So in the second region, moment 2 is equal to the same terms of the first region, minus f times r times sine of theta minus pi over 2. That's my moment in the second region. Now I'm going to move to the next page, and we'll start putting all of that together. Now, let's go back to the picture a minute. Now, I'm going to be writing deflection here because of this one, deflection here because of that one, deflection here because of that one. I've got to write 3 different deflection equations, which means I'm going to need to take 3 different partial equations. And so I'm going to go ahead and take all my partial derivatives at once. And so my partial of moment number 1 with respect to RBX is just minus r sine of theta. My partial of moment 1 with respect to RBY is r times 1 minus cosine of theta, shown here. My partial of moment 1 with respect to MB is a minus 1. Now, eventually, I want to calculate the deflection right here in the structure. And to calculate the deflection right here in the structure, I'll need to take a partial with respect to f. So I'm going to go ahead and do that now while I'm taking my partials. In the first region, though, the partial of m1 with respect to f is a 0, okay, because load f does not appear in this equation. Notice it will appear in the m2 equation. Now, when I take my partials with respect to m2 for all of these earlier terms, I'm going to get the exact same partials, okay, and I will get a partial due to f. And so my partial of m2 with respect to RBX is the same because of that m1 term. And the same here. And the same here. But I do have a partial of m2 with respect to f coming from right here. It'll be a minus r sine of theta minus pi over 2. Minus r sine of theta minus pi over 2. Now, here in some shorthand is what we're going to be solving. We're going to take the integral, or we're going to take the energies over region 1 and region 2, moments times the partial, which, and we have the m1 equation above. We plug it in right here. We have the partial of m1 with respect to the x load. We plug it in right here for region 1. And we're integrating from 0 to pi over 2. Then in region 2, we're integrating from pi over 2 to pi. Of moment number 2, we have that formula right above, and the partial of moment 2 with respect to the x load. In both cases, we replace dx with rd theta. But now we take this deflection equation, since we took our partials with respect to RBX, that will give us the vertical deflection at the place where RBX is applied. That's what this whole thing will give us, the vertical deflection because of load RBX at the place of RBX. But we know that vertical deflection is 0. So we set it equal to 0. After we do all of the integrals, and it will be somewhat painful, after we do all the integrals, we're going to be able to solve that for RBX. We do the same thing except we use the partials with respect to RBY. That changes the equations because the partial with respect to RBY was an R times 1 minus cosine of theta instead of a minus R sine of theta. We take our partials with respect to RBY and plug them in here and here next to the moment 1 equation and the moment 2 equation. Do the integrals. This will give us the deflection toward in the vertical direction because RBY is vertical at the point where RBY is applied, but we also know that deflection to be 0. So we set it equal to 0 and we'll solve for the unknown variable RBY because it will appear in this equation. Then we do the same thing when we modify our deflection equation by using the partials with respect to that moment, MB. This set of terms will give us the slope deflection, or the slope of the beam at the place where that moment is applied. But we know the slope at the cantilevered end is 0, so we set it equal to 0. And then we do all of the integration, which again is going to be big, ugly, and tedious. Okay, but we do that integration and we solve for MB out of this equation. Okay, so in effect what we're going to be doing, as I said here, is we're going to solve these three equations for RBX, RBY, and MB in terms of the applied load F and the radius and EI and other things. Now, do notice one thing. I left the 1 over EI's off of both of these integrals. Why? Because I knew I was going to be setting that equal to 0. And so since I'm going to have, so I can divide both sides of this equation by the 1 over EI term and make it go away, only because I'm setting these equal to 0. Once I've set my 3 deflection equations equal to 0 and solve for my 3 unknown reactions, then I can take my energy equation again, but now solve for the deflection at point F. I've still got to integrate over the entire structure, okay, but now I'm going to use partials of M1 and M2 with respect to the applied load F. I put the partial of M1 with respect to F right here. I put the partial of M2 with respect to the applied load F right there. And in this case, I don't know the deflection. I actually want to solve for the deflection. So I plug in the 4 equations, I do the integration, I simplify from some. What this equation will give me is my deflection at the point where load F is applied in terms of the load F, the radius, but also in terms of these 3 unknown reactions. Now what I'm going to do is go back up to here, these equations that I solved for, and plug those or substitute those into equation 2. So I'm going to take all the equation 1 stuff, substitute into equation 2, and I'm going to get the deflection at load F, at the place where load F is applied, in terms of load F and in terms of the radius of the beam R. Going back up here, so this one is somewhat long and we still haven't even really done the integration, we've just implied it. I turn my cantilevered support into its equivalent reactions because they are over-constrained. I then take my partials with respect to these reactions and I solve for the deflection here and set them equal to the known values of 0 in all 3 cases, which lets me solve for these 3 values, the forces. Then finally I take my partials with respect to F and I can calculate the deflection at the top of this half ring structure. I do have a MathCAD document that crunches out all the numbers, and I'll be showing that in another video.